live. All right. So lesson 402, a continuation of lesson 401 in a way, because we're going to keep finding areas, perimeters, and we saw a bunch of formulas in 401, and we had a nice homework where we were practicing that, and 402 is kind of the same thing. You could say we're going to practice the art of analysis, where analysis by definition means breaking things apart into its little pieces so you can figure out the answer. So anyway, there is the lesson, the guided notes for this lesson, which are in the link, or not the link, in the description below there is a link, and then the homework set is also there too. I think it's like 15 problems this time. Not so bad really. And then here we go on the lecture. So let's start. I got, I think 4, yeah, it says it right there. 4 examples this time. So here's a nice problem here. What do we got here? Find the area and the perimeter, so it's a 2 for special, of this, what's called a Norman window. Must have been built by a guy named Norman or something, right? So if you think back to all the area formulas that we looked at before, you'll say, I don't remember having a formula for a Norman window. And it's like, no, we didn't have a formula for a Norman window, but that's okay, because we can kind of recognize that this is kind of like half of a circle sitting on top of a rectangle, right? So you just kind of cut that right about there and say, yeah, I'll just have to treat this as 2 different shapes. So maybe we'll start thinking in terms of area first. Maybe I'll do area over here. So we're going to have to think of the area of like the rectangle part, and then we're going to have to add on the area of the, not really a circle, but a half circle part, right? So to do the area of the rectangle, you do length times width. And you say, well, I know what this is. It's 1 meter times, and then I know what this is, or wait a minute, do I know what this is? You don't want to use the 2, right? Because the 2 goes all the way to the top. We don't want to use the 2. You got to be a little careful when you're playing with this stuff. We need to figure out, hey, that's not what I wanted to do. Come on, man. Okay, what I wanted to do is get rid of that. Okay. So we got to figure out the height of that thing. Well, how are we supposed to get the height of that thing? Well, you'd have to kind of subtract off however tall this piece of the thing is, this half a circle. How tall is that? Well, that's also known as the radius, right? Can we figure out what the radius of this thing is from the center out to the edge? And we can, because it would have to be the same distance here, right? The same distance here, assuming I drew it all nice and perfectly in the middle. And you can look down here and say, well, if it's a meter all the way across, then the diameter of this circle is a meter, and that means that the radius of this thing is half a meter. So where should I shove this in here? R equals 0.5. I'm going to shove it right there. R equals 0.5. And so that, again, that's the distance not only from here to here, but it's the distance from here to here, it's the distance from here to here. It's from the center of the circle to any point on the circle, that's the distance. So if that's 0.5, basically from here to here, then from here to here, it would be 2 meters minus 0.5. So that's a 1.5 meter height. That's what I would use over here to get the area of my rectangle. Plus, now I need the area of the, not quite the circle, it's a half circle, really. You know, this thing up here, that's half a circle. So what I'll have to do is I'll have to say, well, you know, I know that the, let me just do a little, I know that the area of a full circle, remember this formula, or look it up if you don't, pi d squared over 4. Some people use pi r squared, that's fine too. So pi d squared over 4. If I use this formula, I want to plug the diameter in. So the diameter is a full meter over 4. And so pi times 1 squared over 4 is pi over 4. But we only have half a circle, so really we should take half of that to find that the area of the half a circle is, well, pi over 8, really. And so I'm going to add that here. And so what is our area of this whole window? 1 times 1.5 is 1.5. Add the pi over 8. And did I do this before? I hope so. I did. When I plugged in numbers on my calculator and I forced it to give me a decimal, I got 1.8927 if I want to use 5 sigs, and that would be squares, square meters, because we're measuring in meters, square meters. So yeah, you just break the problem into 2 parts. Perimeter-wise speaking, let's think in terms of perimeter over here on the other side. Well, I would have basically, let me use a different color for this maybe. That looks like a good color, I guess. I'd have this distance, and then this distance, and then this distance. That's part of it, right? So that would be, it's 1.5 meter plus a meter across the bottom plus another 1.5 meter plus. And then comes the tricky part, because you got to figure out, oh, okay, that's like round. So you got to figure out this part here. So, well, remember for circles, the circumference of a whole circle was pi times the diameter. So here, it would be pi times the diameter is just 1. So the circumference of the whole circle is just pi. But we have, oops, this one. But we have half of a circle, which means that the circumference, not for, I shouldn't really say it that way. I should say it this way. The upper part of the circle would be pi over 2. Half times pi is pi over 2. So coming back up here to finish our perimeter, we got 1.5 plus 1 plus 1.5 plus pi over 2. And when you work out the numbers on your calculator and you force a decimal to come out of it, I got 5.5708, and this is just regular meters. Okay, so that's kind of how you work these things out. You just kind of say, well, you know, don't have a formula for that shape exactly, but I do know how to play with rectangles, and I kind of know how to play with semicircles, so you break it into a rectangle and a semicircle and you fly. 1 down, 3 to go. All right, what's going on here? Looks like a ring. It says find the area correct to the nearest square foot of a 4-foot wide path that goes around a big garden that's 400 feet in diameter. A 4-foot wide path going around a garden, huh? Well, this must be the 4-foot wide path. So I know that this is 4 foot across like this. It surrounds a garden that's 400 feet across. So think in terms of where the center is, because the diameter has to go right through the center, right? So the garden itself, that would be inside of the sidewalk. The garden itself has a 400-foot diameter. Okay, and the path has a 4-foot width to it, so we need to find that shaded area. Well, it's a shame we don't have a formula for a sidewalk. That would be called an annulus, I guess. It'd be a more official name for that, annulus. But that's kind of okay. We can build this. And the point of this problem is sometimes you build things by adding areas together, like in the previous problem for the Norman window, we added a rectangle plus half a circle. Here we're going to subtract, really. Think in terms of, we have a big outer circle. That would be if you came all the way out to this edge, right? A big outer circle with a hole punched in it. Just like somebody took one of those hole punches and went chunk. So what we can do is we can subtract then. We can take the area of the big outer circle and then subtract the area of the hole, and that would leave the sidewalk. So let's see now here. For circles, we know that the area of a circle is, again, I like this formula, pi d squared over 4. You could say pi r squared if you want. I'm going to say pi d squared over 4. So the outer circle, arrow, I'm not going to say equals, the outer circle has a diameter of what? See, what you do is you follow your formulas, and then you have to kind of look at your diagram and try to figure out, well, what am I trying to put into this formula here for d? What is the diameter across from here all the way to the outside, right? All the way to the outside. Well, actually, I should say it this way. The diameter is 400 feet on the inside. To get to the outside, you'd have to add 4 more feet over here, but you'd also have to add 4 more feet over here. So it's 400 feet plus 4 plus 4. The diameter of that outer circle is 408 feet. That gets squared, you put it over the 4. Minus. Now we can subtract the whole. Pi times, and we know that the diameter of the hole is exactly 400 feet. So we just use a 400 for our diameter. That gets divided by 4. And actually, that's pretty much it. We just got to crank that out. Now I'm going to get a little bit of algebra-y on you, and I'm going to say, hey, you know what? You know what? This is like algebra, man. This is like factoring, man. This is like I could pull out a common factor, man. Pull out a pi over 4. And what are you left with? Well, from the first term, come on you. You're left with a 408 squared. So write that down. And then from the second term, you're left with a 400 squared. So write that down. And I showed you this partly just so you kind of train your eye on this whole factoring thing. You get used to looking at things, but also because it's easier to enter that on the calculator. Because all you got to do in the calculator is go 408 squared minus 400 squared equals times pi divided by 4. And when I did that, I got a nice answer of sidewalk. Forcing decimals out of the deal. Let's see. I have it right here. Where did I get? I got, well, my calculator, for 5 sig figs, I went 5076.8. But if you look at the original problem statement, it says to the nearest foot. And you got to pay attention to, you know, what are people actually asking you for? If they want the nearest foot, then you give them the nearest foot. And so to the nearest foot, it would be 5077 square foots. 5077 square feet is the area of that sidewalk, which sounds like an awful lot of tiles to me, but I guess that's what it would take. So if you had 1 foot by 1 foot tiles, it would take over 5,000 of them. Holy cow. Well, that's what you get. Okay. Next. Shauna wants to build a hexagonal, 6 sides, a she shed. If the outer sides each have a length of 8 feet, yeah, put a number on there. That's 8 feet. That's 8 feet. That's 8 feet. You know, if they asked for the perimeter, this wouldn't be bad, right? Just add up 8 plus 8 plus 8 plus 8 plus 8 plus 8. But they didn't ask for the perimeter, they asked for the area. So anyway, we're gonna, what's it say now here? Wants to build the outer stage out like the 8. Okay, what will be the floor area? Neglect the thickness of the walls. Okay, so find the purple area, basically. Now, how to go about this one? Well, before you start cranking, what you want to do is just take a second, or maybe a few seconds, and just kind of think, wow, what are all the things I could do here? There's lots of different strategies you could follow here. One idea you could, well, I don't think purple's going to be a good color for this one. Let's use black. One idea you could do, I don't know, for some reason this is the first one that occurred to me, as I said, you know what, I got a big old rectangle in there. And then these are 4 identical triangles. So if I found the area of the rectangle first, and then I found the area of one of these triangles and multiplied by 4, I'd be in pretty good shape. But that's just one idea. You don't have to do it that way. What's another idea? Here's another idea. See what you think of this one. Try to draw like, this is going to be tough, but try to draw like the circle that this thing would be in. Oh boy, that was tough. Try to draw the circle that thing would be in. So, and then subtract, remember we have a formula for the area of these sectors. You'd have 6 sectors around the outside. So, you could figure out the area of the sector because we have a formula for it. We know that this has to be 60 degrees, right? So we could figure out, okay, I got the, well, we'd have to get the radius. But once we solve for the radius, we'd be able to figure out what the area of the sectors were. Once we had the radius, we could get the area of the circle. So we could do the circle minus a bunch of sectors, I guess. That's an option. Okay, let's see if I can erase just these little things here. That'd be cool. Awesome city. Okay. What's another option? Oh, this one I really kind of wanted to do this one. And I was thinking 2 trapezoids. Wouldn't that be fun? Right? Because to get the area of the trapezoid, all you really need to know is, well, you would need to know this height, but and then you would need to know this. I know what this is, though. Can you see what this has to be? Well, I'll show you what that has to be. Hexagons, if you join the opposite sides, they're basically made up of 6 equilateral triangles. That's worth writing down. 6 equilateral triangles. Which means that if that side is 8 foot and that side is 8 foot, well, equilateral triangles means all the sides are the same. So that's an 8, 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 that's an 8. And so that means that it's 16 feet across there. Woo-hoo. So you could play with this as a trapezoid. I got a side of 8 feet. I got a side of 16 feet. Of course, I still got to figure out what this height is. So, and one other thing you could try. You could say, well, you know, I'll just do the brute force. I'll figure out, how would you figure out that height anyway? Well, remember, all these angles are 60, so that's a 60 degrees. So you could do like a SOHCAHTOA. You could solve for this height by using sine of 60 degrees equals h over 8. And once you had that, you can, once you know the height, you can do 1/2 times the base times the height to get the area of this triangle, and you can multiply by 6. So just all I'm doing here is just saying there's more than one way to skin a cat, right? There's many cats can be skinned in many different ways. I'm going to go back to what I said before, 6 equilateral triangles. I'm going to say, wait a minute, don't you remember we had a formula for the area of an equilateral triangle, and it went like this. Went like what? Come on, where'd I put it? Oh, here it is. It went like this. A squared times the square root of 3 over 4. Where A is the side of the length. This is A. The side of a length. The length of a side. So A is 8. We don't have to solve for no stinking height. We don't have to do no stinking SOHCAHTOA. Every one of these triangles, and there's, 6 of them. 1, 2, 3, 4, 5, 6. Has sides of 8. Each one of them has an area of, put the 8 in there, squared times the square root of 3 over 4. Turns out that simplifies quite nicely to 16 square roots of 3. We have 6 of these triangles, of course, so you'd have to multiply that by 6. And so you get that the total area of the hexagon is 96 square roots of 3. Or if you'd like a decimal out of that, and I bet you would, you'd get about 166.28 square feet using 5 sig figs. Oh man, so hard to not smudge these things. Okay, 166.28 square feet. That would be the area of the she shed. And so just, to help yourself think about this, say, well, if I had like a square little bedroom with 12 foot by 12 foot, that'd be 144. So that's bigger than a 12 by 12 bedroom in terms of raw floor space anyway. Okay, cool. Oh, I had fun with that one. I hope you had some fun too. The moral of the story is be creative, break things up however you want to. And sometimes I would say, look, don't just go with the first thing you think about. You can brute force your way through life like that. Just go with the first thing you think, and maybe you have to solve for the height and blah, blah, blah. But sometimes it's cool to just kind of, think about it a little bit more, and then you say, oh, wait, there's a shorter way. There's a shorter way. All right, one more of these examples. Now that's a funky looking boardwalk, right? It's a boardwalk. Step 1, imagine a really big boardwalk. Step 2, find its perimeter. Okay. Now I was just having so much fun finding areas that I can't help but think about the area for a second. Imagine if you had to find the area, what would you do? Well, it looks very tempting to sort of take that as a little mini rectangle, take that as a triangle, right? We've got the dimensions for these things. We can figure it out. That looks like half a circle. Okay, so you could take that area, that area, that area, and then here's my real question. How would you do the inside? Would you break this up into like maybe, well, I suppose you could call that a trapezoid, and then you could call that a triangle, and then you could call that a rectangle, right? Could break it up into 3 pieces like that, I suppose. Here's another idea. What do you think of this? Think of it as a big old rectangle subtracting this trapezoid. Because then you only have to do it in 2 steps. You get the trapezoid and you got the height of the trapezoid here and all this stuff. Yeah, that's okay. That was fun. That was fun. Yeah. But we're going to move forward. What we're asked for, really, is we're asked for the perimeter. And that just means walk around the outside and get the distance. So I'm going to start here, and I'm going to keep going. There's 20. This would have, right there, the dimension is 10. So add 10 plus. Now I got to walk from here to here. It looks like that's got a length of 30. It says it right there. Then I'd have to walk down to here again. So that's another 10. Now I have to walk across here. Looks like they labeled it as 20. So you just got to kind of keep track of yourself here. Keep going, keep going. Now I got to walk this distance, which is labeled as 20 plus. Okay, this is going to take a little more work. We'll have to stop and get a formula for like playing with circles. I'll do that later. Let me just call that A for now, okay? Just kind of do that. I'll get back to that. I want to keep walking around first. So I see this 20 here. Okay, cool. So plus 20 plus. All right, now I'm going to have to go across a hypotenuse, which I could stop and figure that out now, but I don't want to. So I'll save that for a little bit later. Now let's walk along this distance here, which is given as 40. And then, oh, for heaven's sakes, they didn't give us that. We're going to have to figure that one out too. So I don't want to figure it out right now. I'm going to save it for later. So I'm going to call that distance C. And I'm noticing that this distance here is not exactly given to us either. So I'm going to call that D. And then here's another one of these triangle things we'll have to work with to call that E. But then add 20 to get to there. Oh, and by the way, what I should have been doing is saying plus B plus C plus D plus E, right? So this is my answer for the total perimeter. I can simplify that a little bit by just saying, okay, let's add all these numbers. 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120, 130, 170, 180, 190. So the perimeter is equal to 190 plus A plus B plus C plus D plus E. So one thing at a time, getting the A, the B, the C, the D, the E. I'm going to look at the A. Well, it's half a circle. So remember, circles have a circumference of pi times the diameter. The diameter of this thing would be, well, it's 30 to go halfway across the circle, so it would be a diameter of 60, really. And then the other thing is, we've only got half the arc, so we want only half of that. So really that comes out to 30 times pi. And you punch numbers, you get decimals, and what I get? I got 94.248. I like 5 sig figs. 94.248. So you just kind of hang on to that. Maybe get a new color out and then say, okay, let's do B. Well, B is the hypotenuse of a really nice right triangle, right? So we can do the old Pythag theorem. So leg of 40 plus, I need this leg here. Let's see, what would that be? That would be the same as this distance, right? All the way across. 20, 30, 40, 50, 60, 70. That's a 40 squared, that's a 70 squared. Those are the two legs, and that would add up to the hypotenuse squared. Remember the hypotenuse. The hypotenuse always goes on the right. Always, always, always. But B is the hypotenuse, so it goes on the right. And you've done this before, so maybe you'll trust me when I say that when I took the 40 and squared it, and I took the 70 and I squared it, and I added them up, and then I took the square root, my calculator told me, because I have a nice calculator, it told me 10 square roots is 65, and if you got the calculator for the course, then you have a nice calculator. But then if you say, give me the decimal, please, you get about 80.623. Did I say that right? Yes, I did. 80.623. So that's the B. Just got to work out the C, the D, the E. New color. Oh, yeah, let's get green. I'm going to get green with this one. So working out C. Well, once more, that looks like the hypotenuse of a triangle, right? Think in terms of this triangle right there. C would be the hypotenuse of it. And so it would have one leg. This leg would be 15. This leg is also 15 because it says it right there. Equals the hypotenuse squared. And so when you work this one out, I'm sure you trust me, we'll get, actually the nice answer is 15 radical 2, which if you force a decimal out of that, you get about 21.213. We're getting there. I'm kind of in the mood to do E at the moment, just because it's also one of these hypotenuse dealies. So you'd say, well, I got one leg is 20, so 20 squared plus this leg again is 15. 15 squared equals, that would be E squared. And I worked this one out, and what did I get? I got actually a perfect 25. 25.00000. Okay, but now we got to get D. What color do you use for a D? Suppose we haven't used red very much. How am I going to get D? Well, let's see. What I've got is I've got distances here and here. I've got distances here. And I'm kind of missing this one. But let's look to the other side of the rectangle here. I got this distance. And actually, because it's a radius of 30, I know that that's 30 and that's 30, and then that's 20. So the total distance coming down this side would be 20 plus 30 plus 30 plus 20. That's 100. So actually, this is going to be a total of 100. So 20 plus 20 plus D plus 15 equals 100. Oh, that's a lousy place to write that. 20 plus 20 plus the D plus the 15 has to be equal to 100. Again, the reason being that on this side, I got 20 plus 30 plus 30 plus 20 is 100. So I got, this has to be 100 too because it's a rectangle. 20 plus 20 plus 15 plus D is 100. And if you solve that out real quick, you'll get D must be 45. Cool. We've got enough information to figure this out. So now you take your 190 plus A plus B plus C plus D plus E, and you work those all out, and I got a perimeter of just about 456.08. using 5 sig figs, and that would be in meters. And that would be the answer. So maybe I'll just call it out like this. That would be the answer. Okay, so I hope you're in the mood to have a little more fun with these composite areas, just funky shapes. Again, just getting used to our formulas so that we, the more you use them, the more you have them at the ready, the more you're comfortable you are with all of this kind of stuff. I think we got volumes coming up next. So why don't we quit right about there? Somehow.